Hello and welcome everybody to the course Crystal Engineering Chemistry Beyond the Molecule. In this video I will present you, I must say, my special favorite topic in crystal engineering. I will show you how you can use this element deuterium is really nothing, to tune and modify molecular arrangement in solid state. Well, we have seen, I've shown you in several videos that you can use strong hydrogen bonds, crystal engineering. You remember dicarboxylic acids or carboxylic acids. We can use strong halogen bonding, for example, iodine, nitrogen. We can use weak hydrogen bonds. I've shown you, for example, acetylene or something else. We can use weak halogen bonding, chlorine, for example. All these units are successfully usable in crystal engineering. And also fluorine substituents. I've shown you by using fluorine substituents you can increase the acidity and you have repulsive interactions between fluorine substituents, also useful in crystal engineering. Now, question, what's going on if we reduce the dominating substituents? Strong hydrogen bonds, strong halogen bonding, weak fluorine. So we reduce the dominating type of substituents and we look what happens if we use deuterium substituents. What do we know about deuterium? First of all, it is the smallest possible exchange of an element on a molecule. So it's an isotope. But big difference to all other isotopes. Only deuterium has its own symbol in the periodic table. No other isotope you will find in the periodic table, only deuterium. So you see it has a special character. And you know you can use it in spectroscopy, NMR, IR, and so on and so on. But I would say, if you speak with some colleagues, if you speak with scientists, special organic chemistry or inorganic chemistry, I would say most of them stated out deuterium, so HD exchange, has no influence on the crystal structure of chemical compounds. I would say nearly everybody said this is a typical rule. Yes. Well, let's think about it. Have a look on water. Here are some values, important temperatures. This is the melting point. You see you have a difference around about 3.5 Kelvin. Look to the boiling point. There's a difference also 1 Kelvin. And really amazing, so from my point of view, I saw it the first time, is if you look to the difference of the density. Well, with this round about 7 Kelvin difference. And this difference leads to a very funny picture. See it here. This is a typical picture if you have, a cocktail with ice. Aperol Spritz with ice, you see something like this. Well, more red color. Anyway, So the ice is swimming. On the left side, the liquid is normal water, and the ice you see here, this is solid heavy water. And this is exactly what you see if you have such a big difference in the density. So heavy water is not swimming. This is solid heavy water is not swimming on water. So this is really amazing, I would say, huh? And well, deuterium was discovered in the early 30s. And some years later, you see it here, 39, the first group, this was Robertson Ubbelohd, especially Ubbelohd, was one of the scientists who was really interested in this topic. They analyzed the crystal structure of oxalic acid, and they analyzed the hydrate, and they really were a little bit, how shall I say? It was really amazing for them because they saw there's a difference in the cell constants of deuterated and non-deuterated structure. This was 39. And this former scientist said the reason must be that switching from water to deuterated water, you have a new molecular aggregation in solid state. And you see it here, several years later, 53, 67, we were able to really determine the crystal structure. And they saw the former scientists were right. We have only the different cell constant, but they assume there must be different molecular aggregation. That's really right. Have a look here. This is ice catch from hydrated oxalic acid, and this from deuterated oxalic acid. Try it by our own. Have a look here. Wait, here. This is, if you look into mercury, using mercury, and now we have here our hydrated oxalic acid. And here is our deuterated oxalic acid. So in the first moment, from my point of view, I cannot see a really difference. No? Okay, what we must do is here click here on packing. So this is a packing, hydrated. We can see here, for example, the layers, different layers here. One is one layer, we're all parallel. And here is the second layer. And we make the same here in the case of a deuterated. Well, when we say also different, or for example here, we see also different layers here and here. This is one layer. One all parallel, and here is the second. Once again here. Well, now this is the first view. I'm not sure if you can really realize that there is a difference in the crystal packing. I'm not sure. So what we must do is, if you really want to confirm this suggestion, have a look on these planes. What we are doing now, we calculate planes. This is very easy here. A new plane. So, cluck, cluck, and cluck. Oops, oh, sorry, we must pick atoms. So once again, cluck, cluck, and so oxalic acid is a planar, so we need only 3 atoms. Okay, and we need a second plane from this here. Cluck, cluck, and cluck. So we have two planes, and now have a look to the angles between the two planes. Click here on your mouse, right, measure angles, click on one plane, on the second plane, and we see an angle around about 63 degree. Okay, now we make exactly the same, keep in mind 63, so we make exactly the same in the case of the deuterated compound. Here's our cell, a new plane, clack, clack, and da here. Schon wieder. Once again, only. You must always have a look on this picking mode here, no? Clack. Yep. And the second plane, sometimes it's helpful to change the color. One, second and third. So, and now measure the two planes and have a look. 73. Yes? I think this is really a clear value. We can measure the angles between the planes and very nicely we can see here, oops, this is difference around about 10 degrees. Yeah? Going back. So this was the first example that HD exchange has an influence on crystal packing. And if you look in the literature, such effect, phenomenon, is called isotopic polymorphism. Different polymorph by switching the isotopes. Okay, what is the background? The background is called Uberlud effect. Well, what we must look is here on the potential, energy potential. And what we see is that we have a lowering here of a 0 point energy by switching from hydrogen to deuterium. This is all. This is the background. This lowering of a 0 point energy. And this has an effect. If this is a lower energy, XD bond is stronger. And the deuterium acceptor distance is elongated. Well, how can you use it? This effect. We must think about what are suitable compounds. Suitable compounds are general polymorphs. If you see a compound crystallized in different forms, types of molecular aggregation in solid state, when you can use probably HD exchange to switch from one polymorph to the other or to design a new polymorph. If you have a crystal packing, noticeable molecular aggregation with, I would say, strange, interesting, remarkable features, then have a closer look on this molecular aggregation and think about if you can use HD substitution to modify the crystal packing. Or sometimes different crystallization pathways could be observed. Sometimes competitive crystallization pathways. Sometimes you can use HD exchange to control this crystallization pathways. Units to play around are hydrogen bonds, I will show you, and general weak interaction. Why hydrogen bonds? We talk about this Uberlud effect, this lowering of a 0 point energy. So, have a look at the potential energy curves of hydrogen bonds. You see it here, 3 different types. This is typical, this is X, an acceptor. This is a strong hydrogen bond. Well, okay. And here you see the difference if you switch from hydrogen to deuterium. So you see here the probability of a hydrogen, yes, the density distribution of hydrogen. So here in the region of X, in the region of A. In the case of deuterium, the density probability is located in the near environment of X, and this could be useful in the case of hydrogen bonds. For example, trifluoroacetic acid tetrahydrate. Yes, an acid, strong acid, hydrated acid. If you look to the crystal structure, you will see this compound is ionic. Here is our anion, and you see here is our cation. Cation is hydrated, plus a lot of water also. If you look in the case of a deuterated compound, then you will see this is exactly what I've written here in the title. This is a neutral species, not an ionic species. First. The second is, have a look here on the solvents. In one case, looks like this picture. In the case of a deuterate compound, this is the aggregation. Do you see a difference? Do you see the difference between the two aggregations? Have a look. The orientation of the water molecules. Okay. Where is called, if we have such a ring system, molecular aggregation of water, yes, this is called homodromic arrangement, yes. Always one proton of the water molecules is involved in the ring. This one, this one, this one, this one, this one. And if two hydrogens, protons, are involved in the ring of one water, it's called heterodromic arrangement. Now, once again, have a look on the two pictures. In this case, all these cages, which rings, have homodromic arrangement. And in this case, you see both. Here's homodromic, here, and in this case, heterodromic. Nice examples how you can modify, switch the molecular aggregation into solid state, only by switching from water to deuterated water. Next example. Look to a metal organic compound. This is a tetrachloro gold compound. This is crystallized here with an organic compound. And well, we can have a look in mercury. Here, oops, now we're only looking to the molecular structure. This is the molecular structure of this compound. Yeah, you see here our anion, typical planar for the tetragold or aurate anions. And now have a look here on this organic compound. What we see is strongly symmetric. And if you measure the distance, you will see it's exact. Oh no, it was wrong. if you measure the distance, here you will see this is exactly identical. With the same distance, there's no difference. Going back, exactly what I've seen here. No? Two-fold symmetry, and the hydrogen is exactly located in the middle of oxygen contact. And you see very nicely linear configuration. Okay, what happens if you look now to the deuterated species? No? This is here. In this case, you see directly our mercury doesn't line up here a bond, because he said, well, the distance is too long. But anyway, what we see much more interesting is the symmetry. Very nicely here is the symmetry, which is not linear. And if you look to the bond length, the length context with one, the second is here. Well, you see, this is a difference. There's a difference in the distances, oxygen, hydrogen, and the second thing you see different in the angles. I don't know here. Cluck, cluck, cluck. 127. And why? This is exactly what I've said about the Oberlud effect. Lowering of a 0-point energy. And now the hydrogen bond is now a little bit shifted, and the deuterium is more closely to one of the substituents. Next example. Okay, this were example for, I would say, strong or moderate hydrogen bonds. Another examples, pyridine. Pyridine is a well-known compound. Everybody knows it. And if you look to the crystal structure of pyridine here, this is if you open mercury and look to the crystal structure of pyridine, well, the first thing what you see is 4 molecules of pyridine. And if you click here on packing, this is the cell of pyridine. So you see several pyridine are inside, I don't know, 16, 8, I don't know, 12, whatever you want. Right, we can have a look here, display, very nice, more information, structure information, 16 exactly. Okay. So once again, you have 4 pyridine molecules. This is the smallest unit. 4 pyridine, and when you take the symmetry of a space group, PNR to 1, and then we'll get a packing about 16 molecules. Okay, keep in mind. So we have 3 pyridine molecules, and they are called symmetrically independent. So it's not possible by using symmetry to switch from one pyridine, from the green pyridine, to a blue one, a red one, or yellow. There's no symmetry dependency between these 4 molecules. Okay? This is called Z prime. Z prime is the number of molecules in the smallest subunit. This is what I called strange or noticeable molecular arrangement. Yes, 4 molecules in the smallest unit. And well, if you now look to the crystal structure of a deuterated pyridine, plop, everything is fine. You have 1 molecule, the case here, pack and go, 1 molecule, that makes sense. in the smallest subunit here. And now clicking here packing, using the symmetry, you will get a nicely cell. In this case is set as 4. Yeah. This phenomenon of z prime is bigger than 1 is very strange. Once again, we have an asymmetric unit with the smallest part of a crystal structure. When you use symmetry, you see it here, symmetry symbol, no? And you get the whole crystal packing. Sometimes you need only one part of a molecule. I don't know if you have a freehold axis. Yeah? But several crystal structure will you find in the crystal structure database with Z prime, with a Z prime 1, Z prime bigger than 1. And this is a very interesting topic in crystal engineering. Crystal structure with Z prime bigger than 1. Several scientists say, well, this is in this case you have crystallization of the way, you have catched one crystallization possibility which is not the thermodynamic stable polymorph. Some other scientists say, well, we are thinking in models. In the case of crystal structure, we are thinking in space groups. And intermolecular interaction don't fit always with space groups. There's a competition between intermolecular interactions in space groups. Well, you see this is strongly under debate. Okay, next example. Sometimes it is still enough to substitute some hydrogen, not all, by deuterium to get a new crystal structure. This is pyridine N oxide. And if you look to the DSC, if you look to the melting and crystallization behavior of pyridine N oxide, in the case of partial deuterated N oxide, when you will see 2 melting points and you see 2 crystallization temperatures. Normally, you would expect only 1 melting point and 1 crystallization temperature. Well, in this case, you have 2. There's another one and another 1 crystallization temperature. And, well, in situ crystallization at minus 60 degrees, so below this crystallization temperature, the second here, was successful to get a new polymorph of this pyridine N oxide. And you see once again switching here from one space group to the second one. Or last examples, and then I will stop with topic talking about HD exchange, how we can use it. Look to acridine. This is the molecular structure of acridine. Well, in the case of acridine, 6 polymorphs are known, and all of them could be obtained by crystallization from solvents, different solvents and solvent mixtures. Okay, what calculation have shown and experimental observations and investigation have shown that form 2 is the most stable polymorph of acridine. The second thing is form 3 is stable at room temperature, but by increasing the temperature or waiting some days, when you will see that form 3 switch converts to form 2. Okay, form 2 is the most stable, and the second stable is form 3. Well, now have a look. If we crystallize acridine from acetone, we will get form 2. Makes sense? Okay. Now we crystallize partial deuteryl acridine from fully deuteryl acetone, when we will get form 3. And also the case if we crystallize per fully deuterated acridine from fully deuterated acetone, form 3. Okay. What is the reason? What is the background? Once again, look to the energy curves. Energy is always interesting in the case of, so in general interesting, in the case in crystal engineering, always if you have a phenomenon, try to calculate, have a look at the energy. In this case, calculation of the intermolecular interactions, yes? So the weak intermolecular interactions have shown, this is here the interaction CHN, very weak interaction. And if you switch from CH to CD, when you see a lowering of energy. Yeah? And this lowering leads to the formation, dominating formation of form 3. Have a look at the crystal structures. This is form 2. What you see is CHP interactions. This is form 2. In the case from form 3, you have CHN interactions. This is exactly this one here. So this interaction on form 3 is now stabilized by switching to deuterium and leads now to the formation of form 3. Okay, these are some examples, only some examples, to show you how, well, extremely tiny effects are useful for the sensitive, extremely sensitive molecular aggregation in solid state. Sometimes nearly nothing can be used, tiny effects, to switch from one polymorph to the other polymorph. That's it, talking about HD exchange.